Earlier in the course, we were introduced to several properties that systems can possess. In this section, we're going to be revisiting some of these properties, specifically in the context of linear time invariant systems. In particular, for the case of LTI systems, we're going to learn how to characterize some of these system properties in terms of the impulse response. Also, we're going to consider eigenfunctions of LTI systems and see how these eigenfunctions can be exploited in order to solve some types of problems more easily, often by eliminating the need for convolution. Earlier in the course, we were introduced to a number of properties that a system can possess. Also, we saw that an LTI system is completely characterized by its impulse response. Therefore, anything that we could ever possibly want to know about an LTI system must somehow be embedded into its impulse response. So for an LTI system, in principle, it must always be possible to tell from the impulse response of the system if the system is memoryless, or causal, or invertible, or BIBO stable, and so on. Practically speaking, however, the more interesting question is not whether we can extract this information from the impulse response, because obviously we can. The more interesting question is how easily can it be extracted. And as it turns out, this information is often very easy to extract from the impulse response. So what I'd like to do on this slide and the next few slides is consider how we can characterize various system properties in terms of the impulse response of the system. The first property that I'd like to consider is the property of memorylessness. So as it turns out, the way that the memoryless property manifests itself in terms of the impulse response of an LTI system is in the following way. An LTI system with the impulse response H is memoryless if and only if this condition is satisfied. In other words, the impulse response is zero everywhere except at the origin. Now, because of this, the most general form that the impulse response can take on, such that it satisfies the memoryless constraint, is this form here. In other words, the impulse response is just a constant k times the delta function, where k is just a complex constant. And if you remember from earlier in the course, we know that all LTI systems are such that their output is equal to their input convolved with their impulse response. So if we know the impulse response has to look like this, k times delta, we know that we can write an equation that describes the system that looks like this equation here. We have that y, the output of the system, is equal to x, the input of the system, convolved with the impulse response. And what we're saying is if the system is memoryless, the impulse response has to look like this. And we can simplify this expression here because we can observe that convolution is just an integral, so we can pull this constant k out of the integral. And when we do this, what we're left with is x convolved with delta, but because delta is the convolutional identity, we simply get x. So this whole expression here just simplifies to k times x. So if we now ignore the part in the middle, we have that the output of the system is equal to the input of the system times a constant. In other words, the system is what we call an ideal amplifier. It just takes its input, multiplies it by a constant in order to produce its output. So the memoryless constraint for an LTI system is extremely constraining. In other words, if you have an LTI system and it's memoryless, the only thing that it can possibly do is act as an ideal amplifier. And amplifiers are useful in practice for a lot of things, but there's only a limited amount of things that you can do with an amplifier. So practically speaking, the memoryless constraint is quite severe when we're dealing with an LTI system. At this point, I'd like to consider a couple of examples to illustrate how we can use the result stated at the top of this slide. And the first example I'd like to consider is example 4.8. In this example, we're given an LTI system with the impulse response h, which is given by this particular formula here. And because a is a real constant, essentially what we have is a real exponential function times a unit step function. And we're asked to determine whether the system has memory, or equivalently whether it's memoryless. Now we could do this by taking the impulse response and from the impulse response determining the equation that relates the input of the system to the output of the system. And then we could go back to first principles and use the definition of memorylessness and test for the condition in this way. In other words, by using directly the definition of memorylessness. But the idea in this problem is we want to try to do things in a little bit easier way. Rather than going back to first principles, we're going to use our knowledge that the memoryless property manifests itself in a particular way in terms of the impulse response. In particular, a system is memoryless if and only if the impulse response is 0 everywhere except at the origin. In other words, this condition here is satisfied. So this is how we're going to make the determination of whether the system has memory or not. So if we actually graph the function that's given for h, the form that it has is what's shown in the graph here. It's going to always be 0 for negative t because of this unit step function factor, but for t greater than 0, we have a number of possibilities depending on whether the constant that appears in this exponential here is positive, negative, or 0. In the case that a is less than 0, we get a growing exponential function. In the case that a is greater than 0, we get a decaying exponential function. And in the case that a is equal to 0, we have a constant function. But you'll notice no matter which of these three cases applies, this condition for memorylessness is violated. Because for the system to be memoryless, the only place where h can be non-zero is at the origin, right here where I'm pointing. It can't be non-zero everywhere out here. But obviously, no matter how we choose a, it's non-zero for many, many places, actually an infinite number of places other than the origin. So this condition here is violated. Therefore, the system is not memoryless, or equivalently, it has memory. The next example I'd like to consider is example 4.9. In this example, we're given an LTI system with the impulse response h, where h is given by this particular equation here. In other words, h is simply the delta function, and we're asked to determine whether the system has memory, or conversely, whether the system is memoryless. So the first thing we need to remember is that an LTI system is memoryless if and only if its impulse response h satisfies this type of relationship here. In other words, the impulse response is 0 everywhere except at the origin. So if we plot the delta function, what we have is a graph like what's shown in the bottom here. Clearly this function is only non-zero at the origin. Therefore it satisfies this condition here. Therefore the conclusion that we have is the system is memoryless, or equivalently the system has no memory. The next system property I'd like to look at is the causality property. And what I'd like to consider is, for the case of linear time invariant systems, how the causality property can be characterized in terms of the impulse response of the system. So the result that I want to consider is what's introduced at the top of this slide. An LTI system with the impulse response h is causal if and only if this condition is satisfied. And essentially what this condition is saying that I've highlighted is that the function h is causal. And remember, the notion of a causal function, it just relates to where the function has to be 0. In other words, it has to be 0 for all of the negative part of the axis, for all negative t. And incidentally, this is where the term causal function comes from. If we have a function x which satisfies this condition, in other words, it's a function that we call a causal function, where this terminology causal comes from, it's arguably a very bad choice of terminology. Often it causes students confusion because there's no cause and effect involved in this definition, the definition of a causal function. But where this comes from is if you have a function x that satisfies this condition, and this function x happens to be the impulse response of a system, and that system also happens to be LTI, then there's a relationship between this thing being causal, the function being causal, and the corresponding system being causal. But this is a bit of a far stretch. In other words, there's quite a bit of ifs and legalese in the sentence I just said a moment ago that relates the notion of a causal function to a causal system. It would probably be much better if we called a causal function something entirely different, but we're stuck with the terminology, and this is essentially where the terminology comes from. It's because of this relationship at the top of the slide that we call a function that satisfies this condition a causal function. At this point, I'd like to consider a couple of examples to help illustrate how we can make use of the result that was introduced at the top of the slide, in other words, this result here. And the first example I'd like to consider is example 4.10. In this example, we're given an LTI system with the impulse response h, where h is given by this particular formula here, where a is a real constant, and we're asked to determine whether the system is causal. And if we look at the formula for h, you'll notice that e to the minus at is just a real exponential because we're told that a is a real constant, and then obviously u is just a unit step function. So in principle, if we have the impulse response, we could determine the relationship between the input and output of the system. Because the system is LTI, the output is equal to the input convolved with the impulse response. And then from that equation, we could determine using first principles, in other words, using directly the definition of causal for a system, we could determine whether the system is causal. But the intention here is we don't want to go through things in this more long-winded way by going back to first principles and the definition of causality for a system. Instead, what we want to do is we want to use the impulse response to answer this question more easily. So if you recall, the condition that needs to be satisfied for a system to be causal, the condition on the impulse response, is this particular condition here. The impulse response needs to be 0, or h of t needs to be 0 for all t less than 0. In other words, the function h needs to be causal. It needs to be a causal function. So all we need to do is just test this condition. So if you actually graph the function that we're given for h up above here, because the function involves a unit step function, or the expression for h involves a unit step function, this means that the graph for negative values of t is going to be equal to 0. So all we're left with essentially is something that looks like a real exponential for t greater than 0. But depending on the value of a, because we're just told that a is a real constant, we're not told whether it's greater than, less than, or equal to 0. Because of this, there's 3 distinctive kind of behaviors that we can have for this function h, depending on whether a is less than 0, equal to 0, or greater than 0. If a is less than 0, we get a growing exponential. If a is equal to 0, we get a constant function. And if a is greater than 0, we get a decaying exponential. But what you'll notice is in all of these cases, whether a is greater than, less than, or equal to 0, it's always the case that for negative values of t, this function h is 0. In other words, this condition is always satisfied. H is always a causal function. Therefore, the conclusion that we draw is the system is actually causal. The next example I'd like to consider is example 4.11. In this example, we're given an LTI system with the impulse response h, which is given by this particular formula, where we're told that t0 is a strictly positive real constant. So in other words, t0 is strictly greater than 0. And it will turn out to be important later in the problem that t0 is strictly positive. And what we're asked to do in this problem is we're asked to determine whether the system is causal. So the way that we're going to solve this problem is essentially by using the impulse response. Rather than going back to first principles and using the definition of causality directly for a system, we're simply going to use the impulse response directly instead. So if you recall, the condition that needs to be satisfied on the impulse response of a system in order for that system to be causal is the impulse response needs to satisfy this condition here. H of t is equal to 0 for all t less than 0. In other words, the function h needs to be a causal function. So if we go back up to the formula for h up here, what you'll see is we have a time-shifted delta function that's been translated. Because we have either a plus or minus a constant here that's being added to the t, this is going to correspond to a time shift. And in particular, it's going to be a shift by negative t0. The reason why is with a time shift, we have to read it this time shift with the minus sign here. So this would be t minus t0. So the amount we're shifting by is minus t0. So if we were to plot this expression for h, what we're going to end up with is what's shown in this figure in the bottom left. And the important thing is that minus t0 is to the left of the origin because the amount that we're shifting by is negative t0, and because that t0 is positive, this means that minus t0 is negative. So this point here has to be to the left of the origin. And this is important because this will influence our decision about whether the system is causal. So now if we go over to the condition that needs to be satisfied, we need to check and see, is h of t equal to 0 for all t less than 0? Well, clearly this condition is violated because minus t0 is less than 0. This is clearly to the left of the origin, but the function's non-zero at this particular point. So this condition over here is violated. Therefore, the conclusion that we come to is that the system is not causal. The next system property that I'd like to consider in the context of LTI systems is the invertibility property. Now suppose that we're given an LTI system and told that it's invertible. one might wonder if this inverse system is also LTI. Well, as it turns out, this is always the case. In other words, the inverse of an LTI system, if it exists, is always LTI. Now, since the inverse system is LTI, its impulse response completely characterizes its behavior. Therefore, we might wonder if there's a relationship between the impulse responses of an LTI system and its inverse. In fact, there is, and it involves convolution. And in particular, what we have is the following. So if we let H denote the impulse response of our original LTI system, and H inverse denote the impulse response of the corresponding inverse system, then these two systems have their impulse responses related by this particular equation here. In other words, the convolution of a system's impulse response and the impulse response of its inverse system yields the delta function. And this gives us a way we can test whether a system is invertible, because if we're given some arbitrary LTI system with the impulse response H, and we want to determine whether the system is invertible, what we can do is attempt to solve for this H inverse, in other words HINV, in this particular equation here. And if there is a solution for HINV, this must be the impulse response of the inverse system, meaning that the inverse system must exist, because otherwise we wouldn't have been able to find its impulse response as a solution to this equation. So this gives us a way to test for the invertibility of a system. Now, often in practice, this is not the easiest condition to actually test, at least in the form that it's written here, but nevertheless, this result is still quite helpful to know. At this point, I'd like to consider an example to illustrate how we might make use of some of the results introduced on this slide. And in particular, I'd like to consider example 4.12. In this example, we're given an LTI system denoted by script H with the impulse response little h that's given by this particular formula here, where A and T naught are real constants and A is not equal to 0. And it turns out to be important later in this example that A is non-zero. And what we're asked to do in this example is we're asked to determine first of all if H is invertible, and if it is, we're asked to find the impulse response of the inverse system, where the impulse response is denoted by H subscript INV, where INV stands for inverse system. So the way we're going to go about doing this is we're going to try to solve for H inverse in this equation here. In other words, we'll plug in the impulse response of the original system that we're given H and see if there's a solution that we can find for H inverse. And if there is, this means the system is invertible, because if there is a solution, what we found is we found the impulse response of the inverse system. And obviously we couldn't find that impulse response if the system didn't exist in the first place. So we're going to use this equation as our starting point. This one here, if I can highlight it. And the first thing we're going to do is we're going to expand out this star notation in terms of a convolution integral. So that gives us this next line. And then what we're going to do is we're going to substitute the function that we're given for H. So we can substitute this function up above for our expression H in this integral, which gives us this next line. And then what we're going to do next is we're going to divide both sides of this equation by A. And we know that we can do this safely because we're told in the problem statement that A is non-zero. So we don't have to worry that we might be dividing by 0. So we divide both sides by A, which gives us this next line here. And what we're going to do next is we're going to use the sifting property on the left-hand side of this equation. If you look at the left-hand side of this equation, you'll notice that this integral that we're dealing with on the left-hand side is of the form of the sifting property. We have the limits being minus and plus infinity. We have a shifted delta function times some other function, which is this underlined function. So the whole left-hand side will simplify to just this underlined function here, the thing that the shifted delta function is multiplying by, evaluated at the point where the delta function is non-zero. And because this delta function has been shifted by t naught, it's going to be non-zero at tau equal to t naught. So this whole left-hand side just collapses into this underlined expression evaluated at tau equal to t naught. In other words, what's given by this next line here on the left-hand side. And the right-hand side just carries along to the right-hand side on the next line. And if we evaluate this left-hand side at t naught, that gives us this next line here. Now what we do next is we're simply going to substitute t plus t naught for t. So on both sides of this equation, we're going to substitute everywhere where there's a t, we're going to substitute t plus t naught, which gives us this next line. And then if we simplify, this gives us the final line, this one here. And if we look at what we have on this last line, we have an equation for h inverse of t. In other words, we found h inverse of t. In other words, we found the impulse response of the inverse system. Therefore, the inverse system must exist because we found its impulse response. Therefore, the conclusion we come to is this system must be invertible. The next system property that I need to discuss in the context of LTI systems is BIBO stability. In particular, what's of interest here is how the BIBO stability property manifests itself in the impulse response of a system. And in this regard, we have the following result. An LTI system with the impulse response h is BIBO stable if and only if this condition is satisfied. And this condition is sometimes referred to as the condition of absolute integrability. In other words, the function h is absolutely integrable. And what this means simply is if a function is absolutely integrable, it means if you take the magnitude of the function and then you integrate that over the entire domain of the function, which in this case is the real line, this converges to a finite value. This is all it means for a function to be absolutely integrable. So in other words, if this condition is satisfied, the system is BIBO stable, and if this condition is not satisfied, the system is not BIBO stable. And this particular condition is quite useful in practice. If we're trying to determine whether a system is BIBO stable, if we go back to doing this by first principles, in other words, directly use the definition of BIBO stability, this can often be quite tricky to do, especially for more complicated systems. But what this slide gives us is another way to test for BIBO stability in the case that the system involved is LTI. So this can be quite useful in practice, this particular result on the slide. At this point, I'd like to consider a couple of examples to help illustrate how we can make use of the result presented on this slide. And the first example I'd like to consider is example 4.14. In this example, we're given an LTI system with impulse response h, where h is given by this particular formula here, where a is a real constant. So in other words, what we have is a real exponential times a unit step function. And we're asked to determine for what values of a the system is BIBO stable. So the basic idea here is we're going to check to see under what circumstances h is absolutely integrable. In other words, that this integral here converges to a finite value. So to begin with, we first substitute into this the formula on the left hand side, we substitute in for h, the particular function that we're given for h up above here. So this gives us this right hand side. And then what we're going to do is we're going to split this integral on the right hand side such that we're integrating over two subintervals. So we're going to split the interval from minus infinity to plus infinity to two subintervals, one where the unit step function is equal to 0 and one where the unit step function is equal to 1. So the unit step function will be equal to 1 between 0 and infinity. This is the second integral here. And the unit step function will be equal to 0 between minus infinity and 0. So this is the first integral here. And obviously this first integral is just going to drop out because we're integrating 0 in this case. And the second integral, we just have our standard exponential that we need to integrate. So this right hand side just simplifies to this next line because the first integral drops out since it's 0. And then essentially what we have are two different cases for handling the integration of this exponential. The first case, which is maybe the more interesting case, is when a is not equal to 0, in which case we're integrating something that's not a constant function. So we just integrate this using the standard formula for integrating an exponential, which gives us another exponential on this line here. And the other possibility is that a could be equal to 0 when we're integrating this function here. In other words, what we're really integrating is just 1. So in this case, what we have is a slightly different formula. We don't get an exponential, rather we just get t when we integrate. So we just need to simplify each of these two expressions, the one for the case that a is not equal to 0 and the one for the case that a is equal to 0. So first we're going to handle the case that a is not equal to 0, so we're going to try simplifying this expression here. So that's what's appearing on this line right here. This one here. So the only thing that's a little bit trickier we have to be careful about is when we're evaluating the the expression in square brackets here at t equal to infinity. So what we're going to end up with is e to the a infinity, and the question becomes, well, what is e to the a infinity equal to? Well, it depends on what a is. We know that a can't be 0 because by assumption, when we're handling this case here, by assumption a is not equal to 0. So we only have two possibilities. A is either less than 0 or a is greater than 0. And depending on which of these two cases holds, we can get one of two answers for e to the a infinity. Either we can get 0 or we can get infinity. In particular, if a is less than 0, then this exponential is going to be e to the minus infinity, which gives us 0. On the other hand, if a is greater than 0, then this exponential is going to give us e to the plus infinity, which is equal to infinity. So in other words, the only circumstance under which this expression here is going to be finite is in the case that a is less than 0. And in that particular case, what we get is this exponential term goes to 0. In other words, we have this next line here. And of course, the 0 just drops out, which gives us minus 1 over a. Now, we still need to consider the case that a is equal to 0. So if a is equal to 0, then we need to simplify this expression, which is this one down below here. And obviously, this expression is going to go to infinity. Now, at this point, we can combine the results for the two cases that we've considered. In other words, the case that a is not equal to 0 and the case that a is equal to 0. So if I just scroll this up a little bit, in summary, what we have so far is that this particular integral that we're computing, in the case that a is less than 0, we get a finite value, and the finite value we get is this minus 1 over a. And in the case that a is either greater or equal to 0, we get infinity for the result. So the conclusion that we draw here, bearing in mind that what we're interested in is whether or not this value is finite or not. In the case that this integral is finite, it means the system is BIBO stable. In the cases where this doesn't converge to a finite value, the system's not BIBO stable. So what we have then is that in the case that a is less than 0, since this integral converges to a finite value, in particular it converges to the value minus 1 over a, where a is not 0, therefore this is a finite value, the system must be BIBO stable. And in the case that a is greater or equal to 0, because the integral doesn't converge to a finite value, the conclusion we have is the system is not BIBO stable. So in other words, the system is BIBO stable if and only if a is less than 0. The next example I'd like to consider is example 4.15. In this example, we're given an LTI system with input x and output y that's defined by this particular equation here, and we're asked to determine whether the system is BIBO stable. Now we could do this by first principles. In other words, we could go back to the definition of BIBO stability and directly use this definition in conjunction with the equation that defines the behavior of the system, in other words, the equation that I've just highlighted. We could use these two things together in order to test for BIBO stability. But this is not really the intention of this particular example. In this example, we are told that the system is LTI. So since the system is LTI, we know that we can test for BIBO stability using the impulse response of the system. And in particular, we can test the impulse response of the system to see if it's absolutely integrable. And if it's absolutely integrable, the system is stable, otherwise it's not stable. So if we want to do things in this way, we first need to find the impulse response of the system, because we're not directly given the impulse response in this example. So to find the impulse response of the system, all we need to do is take the equation which defines the input-output behavior of the system, and we're going to let the input x be equal to delta. And by definition, the output that we get will correspond to the impulse response. In other words, the impulse response is simply the output that's produced by the system when the input is the delta function. So with that in mind, that gives us this next line here. And at this point, we now need to simplify the integral on the right-hand side in order to find the impulse response of the system. So to do this, I've drawn a diagram below to help guide us in this integration. So we're integrating from minus infinity to t, the delta function. So the delta function is plotted in this graph. And we can make a few observations about this graph. We know that the area under this curve, in other words, if we integrate this function over the entire real line, we get an area of 1. But if we integrate this function anywhere other than the origin, we get an answer of 0 because the function is 0 everywhere except at the origin. So based on this, we can deduce the fact that this function has an area of 1 all concentrated at the origin. So when we're integrating the delta function, either we get an answer of 1 or we get an answer of 0, depending on whether or not the interval that we integrate over includes the origin, where all of the area of 1 under this curve is concentrated. So with that in mind, you can see that there's going to be a number of cases that we'll have depending on what the upper limit t is for our integration. We're integrating from minus infinity, so no matter what, we're always starting at minus infinity. However, t, which is our upper limit of integration, it could be in various places relative to the origin. So the first case would be t is less than 0. In other words, t is somewhere to the left of the origin. In this case, the interval that we're integrating over here, the function that we're integrating, delta, will always be 0, and the result we get is 0. So when t is less than 0, you'll see that the result we get for the integration is 0. Now if t is either equal to 0, which corresponds to this middle case, so t is right touching 0 here, or t is greater than 0, which would correspond to this case here, the bottom one. In these two cases, the origin is included in the interval we're integrating over. Therefore, the area that's concentrated at the origin, the area of 1, gets picked up in our integral, and we get an answer of 1. So this is why when t is greater or equal to 0, the area under the curve is equal to 1. Now at this point we can observe that this multi-case expression here is simply equal to the unit step function, so we can replace this by the unit step. So now we have the impulse response. The impulse response is simply equal to the unit step function. Now in order to determine whether the system is BIBO stable, we simply need to test whether the impulse response h is absolutely integrable. In other words, we need to determine whether this integral here converges to a finite value. So let's compute this. So what we're going to do is we're going to take the impulse response we computed above here, which was the unit step function, and substitute this for h. So this gives us the right-hand side over here. And then we need to simplify this integral. So the unit step function is only non-zero between 0 and infinity, and in particular it's equal to 1. So we can simplify this integral here on the right-hand side to the integral below it. And integrating 1 from 0 to infinity is going to give us an infinite result. So in other words, the conclusion that we have here, because this integral does not converge to a finite value, it basically blows up to infinity, the function h is not absolutely integrable, therefore the system is not BIBO stable. At this point, I'd like to consider another property of LTI systems, namely their eigenfunctions. Recall that in general, each system has its own particular set of eigenfunctions. In the case of LTI systems, however, it turns out that all LTI systems have some eigenfunctions in common. In particular, every complex exponential function is an eigenfunction of every LTI system. Now, a specific LTI system may have other eigenfunctions in addition to the complex exponentials, but we are guaranteed that the set of eigenfunctions for an LTI system must at least contain every complex exponential function. And this is the reason why complex exponentials play such an important role in the study of signals and systems. Now let's look at this eigenfunction property of LTI systems in more detail. For an LTI system denoted by script h, with the impulse response little h, the system always satisfies an equation of this form here, where s is a complex constant, and the function capital H is given by this formula here. Now let's look at this relationship here and look in more detail at what it actually means. So here we have a function e to the st being put into the system script h as input, where s is a complex constant, so this is just a complex exponential function. And the output that we get is simply e to the st, in other words the same complex exponential function, multiplied by a constant that depends on s, where this constant is given by the function capital H. So in other words, we have that e to the st, a complex exponential function, is an eigenfunction of the system script h, where the eigenvalue is given by h of s. In other words, by evaluating this function capital H at the point s, where s is the particular constant that's associated with the complex exponential e to the st. Now just as a comment to the side, it turns out that the integral that appears in this formula, in other words the integral on the right hand side, is of great significance. It's what's referred to as a Laplace transform integral, and we'll be studying the Laplace transform in great detail later in the course, but this is the first point at which it sort of starts to creep into the math. Now, because the function capital H is extremely important, because it allows us to figure out the eigenvalue that goes with a particular eigenfunction e to the st, we give this function capital H a name. It's referred to as the system function or transfer function of the system. And often we'll use the system function when we're working with LTI systems. At this point, I'd like to consider how we can exploit eigenfunctions in order to more easily deal with LTI systems. So consider an LTI system with input x, output y, and system function h. And suppose that the input to the system x can be expressed in this particular form here. In other words, expressed as a linear combination of complex exponentials, where the ak and the sk appearing in this expression are complex constants. Then, using the fact that complex exponentials are eigenfunctions of LTI systems, we can show that the output of the system, which is denoted by y here, is given by this particular formula that I've highlighted. And if you compare this formula to the expression on the right-hand side of this equation, you'll see they're almost identical. The only difference is this formula below has an extra constant being multiplied into the expression, in particular this constant h of sk. So another way to look at what these equations are saying is that if we represent the input to an LTI system as a linear combination of complex exponentials, the output of the LTI system can also be expressed as a linear combination of the same complex exponentials, and the word same here is quite important. Effectively, what this allows us to do is find the output of the system simply by multiplying by a constant, because if we have the input expressed in this way, in other words in terms of a summation of this form, to find the output of the system, all we need to do is just take the formula from above here and multiply it by this h of sk, which is just a constant. So if you're thinking, okay, well now I have yet another formula I need to memorize, in other words the formula in the middle of the slide here, then you've kind of missed the whole point of what we're trying to do here and what the significance of the result of this slide is, which is, notice that we didn't do a convolution in solving this particular problem. In other words, we're given an input to the system, which is x, and we're finding the output of the system y using a formula which does not in any way involve convolution. And this can only be a good thing, because if there's one thing you should learn from this course is that convolution is purely evil. You should avoid it at all costs, and anything that you can do that saves you from having to compute convolutions can only be a good thing. And here what we have on this slide is a way that we can solve a particular type of problem involving LTI systems without having to drag convolution into the solution process. In effect, we've used eigenfunctions to replace convolution with the much simpler operation of multiplication by a constant. At this point, I'd like to consider a couple of examples, and the first example that I'd like to consider is essentially a proof of the result that was just introduced on this slide. In this example, we're going to prove the result that was introduced on the computer slide we were looking at just a few moments ago. So suppose that we have an LTI system that's denoted by the script h, and which has the input x, output y, impulse response h, and system function capital H. And suppose that we can represent the input to the system as a linear combination of complex exponentials, in other words using a sum of this form. So x is our input, and we can represent it in this particular form here. What we're going to show is that the output of the system can then be calculated using this formula here. In other words, this is the result from the computer slide we were just looking at a few moments ago. So to begin with, we just start with the equation which defines the input-output behavior of the system, which by definition is just this equation here. And the first thing that we're going to do is we're going to take x, and we're going to substitute for x this right-hand side here, because we're assuming that we can write x in terms of a linear combination that looks like what's shown in this highlighted expression. So if we substitute this in here, this gives us our next line. And then what we're going to do next is we're going to observe that h is a linear operator, because by assumption h is a linear time invariant system, so obviously it's linear. Because it's linear, we can interchange this summation and this multiplication by the constant ak with the operator h. In other words, we can interchange the order of a linear combination and the operator h. So by doing this, this operator h here moves inside the summation to this place. And now what we have is the operator h being applied to e to the skt. And the thing to note here is that this particular function that the operator h is being applied to is an eigenfunction of the system h. Therefore, the output of the system, when we put this particular complex exponential into the system h, is simply the same complex exponential, but multiplied by the system function evaluated at sk. This simply comes from the eigenfunction properties of linear time invariant systems. So we've effectively shown the result we wanted to show, which is that if the input has this general form here, then the output is going to have this particular form here. And just as a side comment, the important thing to notice here is that this equation 4.48 doesn't involve a convolution. All it involves is multiplication by a constant, because if we compare this equation for the output to this equation up above for the input, the only difference between the right-hand sides of these two equations is that this equation here has a constant factor added in. There's a constant factor that's being multiplied by, which is missing from this equation here. So in order to compute the output, all we have to do is simply insert a multiplicative constant, and that's all. So we're basically converting convolution into multiplication with this particular approach. And obviously, convolution is a much more difficult operation than multiplying by a constant, so multiplying by a constant is very much preferred. Hence the value of this particular equation 4.48. The next example that I'd like to consider is example 4.16. In this example, we're given an LTI system denoted by script h, with the impulse response h, given by this particular formula here. And we're asked to do a number of things. In part A, we're asked to find the system function of the system, where the system function is denoted by capital H. And then in part B, we're asked to use the system function to determine the response of the system to a particular input x, where x is given by this particular formula here. So proceeding on to part A of the problem, we're first going to find the system function capital H. So to do this, we simply use the formula which defines the system function, which is this formula here. So we're going to take the function little h that we're given and substitute it for little h here. So we're told that little h is this particular function here. So we're going to substitute this for little h, which gives us the next line. And at this point we can use the shifting property, because we identify this integral as having the form of the shifting property. We have a shifted delta function appearing in the integrand times another function, this e to the minus st, and the limits of integration are minus and plus infinity. So this has the form of a shifting property integral. And the shifting property tells us this whole integral is going to evaluate to this particular function here, the thing that's multiplying a shifted delta function, for the value of t where the delta function is non-zero after it's been shifted. So this is going to correspond to a value of t equal to 1. So we're going to evaluate e to the minus st at t equal to 1, which gives us this next line. And of course, if we evaluate this, we get e to the minus s. So this gives us the system function for the system, which is what we're asked for in part A of this question. Now I'll scroll this up so we can move on to the next part of the example. In part B of the problem, we're asked to find the response of the system to the particular input x that's given by this formula here. And since we want to use eigenfunction properties to do this, we're going to have to rewrite x as a weighted sum of complex exponential functions. And to do this, we can simply observe that we can use Euler's relation to rewrite this cosine function as a pair of complex sinusoidal terms. In other words, we can rewrite the cosine function like this, as I've highlighted here. And then we can use exponent rules to rewrite this as the second, or this next line. Now once we have x expressed in this form, in other words as a weighted sum of complex exponential functions, in other words we have x written in this form, we can read off the various different coefficients that appear here to write things in terms of a summation. So that gives us these ak values here and these sk values here. And at this point we can now use eigenfunction properties of LTI systems to write the formula for the output. The output is going to be given by this particular formula here. or again, y is denoting the output in this particular example. So we can expand out this summation into the two terms that it comprise it, so that gives us this next line. And then we can substitute the values for AK and SK up above here into this line to get to our next line, this particular line here. And then we can evaluate the function h. There's two places where the function capital H appears, so we can evaluate this function and we can evaluate this function here to give us the next line. And then we can do some algebraic manipulation to manipulate this particular line into the form of the second last line. And at this point we can observe that the quantity in square brackets on this line, in other words this quantity here, is just a cosine function. In particular it's cos of pi t minus 1. So now we have the output of the system. Again, y denotes the output, so we've determined the response of the system to the input x that we were given, and in particular the response is this particular function here. At this point I'd like to make one important observation concerning our approach to part B of this example. In particular, notice that our approach didn't involve convolution. By using an approach based on eigenfunctions, we were able to solve the problem much more easily than we could have with convolution, and this demonstrates the true power of eigenfunctions. Often we can greatly reduce the effort required to solve a problem by using techniques that exploit eigenfunctions.